definition, for example, for local term, you can see in here, for a local term, this is the case for a physical simulation. This is what we do when we are writing a numerical code, CFD code. For example, when we want to obtain the derivative at point ij, this central point, we get by how do we write the discretized version of derivative at this central point? I will get the values at the neighboring points, these 4 points, for example. You might know it. And then I will use these values to try to calculate the gradient. I think you saw this before, right? In your courses, in your undergrad courses or something. So the gradient along x direction, you can use this one and this one. Along y direction, you can use this one and this one, right?
Yes, we saw it in a CFT course.
Okay, in CFD course.
Mhm.
So in order to calculate the gradient, we don't use any non-neighbor point. We don't use, for example, this point. We don't use this point. We don't use this point. This is what we call local term because you're calculating the gradient locally. It's only limited to these points. But in order to calculate the summation that I just represented to you, this summation in this previous slide, uh, it is non-local. You have to multiply all possible Fourier modes relevant to each point. For example, this is my uh, point, but I have to multiply all possible Fourier modes relevant to this point with all other points that are existing in your domain. Just consider that for this point, you have to use all the points. And at each of these points, you have to use all, I mean, the whole Fourier terms at these points. So this is actually the thing that makes it very difficult. You're doing a very huge summation. So if we have, let's say, n numbers of points, you remember that we had a cube with side length L. Just consider that you have n number of points, and you have to write, uh, if you think it as a code, as a numerical code, you have to write two uh, do loops. So you have to write two do loops within each other, and each one goes from 1 to n numbers. So that requires what? N times n number of operations. This n times n number of operations just to calculate the summation. And this will be very huge because if the n corresponds to your physical domain, for example, if you have a very small DNS simulation um, on a cube which has a side length of only 128 points, and these points, of course, they should be very close to each other. Your grid has to be very fine enough to resolve the smallest scales. And these 128 points can capture very small Reynolds numbers. If you want to go to higher Reynolds numbers to resolve more scales in the domain, you have to increase the size. Okay, so every time you increase it, for example, uh, in here you have 128 to the power of 3, which is approximately 2 million. This is 2 million operations. I said that n by n, it is n squared. So in 3D, it is n cubed. So it is 2 million um operations on a just 128 points. 128 points, if you want to resolve all the things inside, it could be a very, very, very small volume that you can actually resolve. So, as I said, if you, for example, use 4096 points, it is 4096 cubed, which is how many? 68,720 million operations. This much operations only at one time step, only one realization of the flow. So to find the right hand side of the equation that we just saw, this is a very simple equation, but the right hand side involves too many operations. It's basically this is basically what makes it very difficult to do, even when you use the spectral method. This is the main reason why it's very much restricted to very low Reynolds numbers, and also you have to consider that this is limited to only homogeneous turbulence. You remember that we said spectral methods are only used on homogeneous turbulence because you have to use periodicity, and uh, um, you cannot you can, it has to be confined. There is no boundary effect in homogeneous turbulence. So again, non-local means that in order to obtain one value of the wave number, you have to multiply by all the values of the wave numbers. Mm,
May
for
I ask
example,
a
if you are,
question?
yes, yes, yes.
I'm just curious about what is the dimensions of this kind of a cube. Let's say 4096 grid
Mm-hmm.
points.
Mm-hmm. Actually, Umit will answer us because I think the paper is related to this cube, right, Umit?
Yes, yes, teacher.
Yes,
Yes. Okay.
the same cube was in the paper also, but I
Mhm.
couldn't remember the dimensions. Also, I wanted to ask that what is the time resolution? In this kind of a case, we are just solving little amount of time, but
Actually, your time resolution again is restricted to your uh,
spatial.
Kolmogorov time scale.
Okay.
Okay, so
Mhm.
Kolmogorov will give you both time scale and spatial scale, right? Length scales.
Yes.
So this time resolution is also restricted to the Kolmogorov time scale as well.
Okay.
That is, I mean, just consider that these many operations. You might remember that we were talking about the flops uh, the last session. Floating point operations per second, flops, right? And we said that nowadays we have supercomputers that can do um, billions of flops. So this is actually that thing. You have to do this much 68,720 millions operations, floating point operations at each time step. That's why we need supercomputers to do these flops much faster for us and to resolve better in time because you need to have a very, very small time step as well. So, yeah, Umit will present those things today to us about this cube thing. So, it's just, again, I want to remind you about the non-local terms and local terms. He said that you have the non-local term. So, for example, if you're interested in just one point in the non-local term, this point in here, that point is get affected by every other points that exist in your domain. It's kind of similar to what you do in vortex method. Do you remember the panel method, the vortex method in aerodynamics?
Yes, I can remember.
So yeah. If you ever had a chance to try this panel method in order to find the induced velocity on one vortex, you have to do the calculation from all the vortices in the domain. So each panel is get affected by every other panels. Actually, this is a problem in any physical application, and it is called n-body problem. N-body problem involves n squared numbers of calculations, which make them very difficult to solve numerically because they all require lots of computational resources. Actually, of course, you can find smart ways to reduce the number of calculations which people already did. You can, for example, use fast multiple methods, which reduces the number of operations from n squared to n times log n, logarithm of n. So summation over um, all discrete values will be required that fall inside the domain. So if we are talking about a simple grid, very simple grid, like the grid that you're seeing like this, if you want to find out the value at point 0, you have to relate all other points inside this domain to the point 0, one by one. And you have a discrete, so this is a summation, discrete summation in this equation that represents a truncation in the wave number space, in k space. Because we cannot go to infinity. We said it before, and we have to cut the wave numbers somewhere. Although, as long as the maximum wave number representing the smallest, very small eddies, Kolmogorov length scales, or those dissipative eddies in the domain that we have, there is no problem if we have covered all of those. But one thing that you have to keep it in mind is that you have to be careful to choose this truncation so that it lies above the dissipation range. It has to be highest possible wave number, which is the smallest eddies. If the cutoff wave number is smaller than the highest possible wave number in your domain, you are basically forcing it to do something else rather than DNS. It is not DNS anymore. It will be something else, and we will talk about it. So this equation that we talk about um, is a set of ordinary differential equations, but still, as Osman said, we have this delta t or dt, and we still uh, need to integrate this into time. And it must be, as I said, it must be small enough to resolve the time scales of the smallest structures. Um, as an example, in a typical spectral DNS study, usually if you have n number of physical points in each direction or each side of the cube, then it represents n cubed number of wave numbers. And then you have a squared n squared that we were talking above. We said n squared. You have n squared. So to simplify 2D, if you want to simplify to a 2D, you have n squared. And in reality, for 3D, you have n cubed. So looking at the equation, at this equation that I wrote in here, we are multiplying um, this u of k prime but by u of k minus k prime. Therefore, you have uh, n cubed times n cubed, which is n cubed squared. So it is n to the 6 operations. So n to the 6 operations will be needed to do the right hand side of this equation at each time step, right? And this is crazy amount of calculation in order to um calculate this. People have tried and they developed pseudo spectral methods not spectral methods, pseudo, or I can write it pseudo spectral, methods, and that kind of reduces the number of computations, as I said, n squared to the n times log n, for example. Several years ago, the largest DNS for homogeneous turbulence was done for this 4096 cube, the physical nodes, I mean. So at each time step, you need to do 4096 to the power of 3. And when I say it is a crazy amount, it is very crazy amount of operations, and it requires heavy parallel computation. So only one question is left in DNS, and it is that how we choose the maximum and how do we discretize the wave numbers. So we said that we have to cut at some point these numbers of waves. So there's this question left in here, and we're gonna see that. So what did we say so far? A spectral method actually converts a PDE, partial differential equation, into a set of infinite number of ODEs, ordinary differential equations. But the problem is that the computer does not know infinity. So you need to cut them at a number like n. And if n is large enough, you still have a very good estimation of the solution. The spectral approximation is uh, depending on the number n and also some coefficients. So these coefficients came from boundary and initial conditions of your problem. So the main idea is that to think about the solution as a summation of sinusoidal waves, sine and cosines. This is what we just understood. We said uh, all of these, and the paper I gave, it's a DNS of 4096 cube, and this is the number of grid points in the physical space. So this Kaneda Ishihara paper. So actually, I guess you uh, read the paper, and a few points regarding how we select this maximum and minimum size of the domain left. So these are all explained actually in chapter 9 of Pope's book. The title of that chapter is DNS, and it is very short. It doesn't actually describe many mathematics and many physics, but it refers all the time to the chapter 6 of that book with too many figures and equations. And actually, in chapter 9, we have a very short recap of practical ways to do DNS, like how we choose the domain size and everything. So I strongly suggest you that you read the chapter 9 of that book. The other extreme, you remember that we said we are doing DNS, but at the other extreme, we do modeling. We didn't study the modeling yet, but we are using some models, for example, eddy viscosity models. These models actually model entire characteristics of the turbulent flow. And at this day and age, we are somewhere that we have to rely heavily on DNS and LES. The modeling is not working. 20 years or 30 years ago, it could be modeling at first. So right now, we will cover DNS and LES first because they are much, much more important than modeling in today's. We have to be updated. And then we will see those details of modeling later. LES is very much related to DNS. We will see LES as well. And then all the modeling stuff that we will see later, like the eddy viscosity models, Boussinesq approximation, K epsilon, K omega, are very quite standards right now. And for complex engineering flows like um, combustion or RANS-based models, Reynolds average Navier-Stokes based models, they are really not working. So you need to do LES, you need to do DNS. We will cover both mathematics and physics of LES. But before that, let's finish this DNS. It's a very short discussion. So we do a lot of homogeneous isotropic turbulence DNS to understand the physics and mathematics of turbulence and to help us develop new models that can be used both in LES and eddy viscosity modeling, for example. So uh, you remember that you had a simple solution domain like this cube with a side length L, and it has 6 faces, and we use Fourier series approximation. That means that we have periodic functions, so boundary conditions on all 6 faces have to have periodic conditions on all 6 faces. The question is how big should be the L number, side length number, and how small should be your delta x, and also how small should be your delta t. Also, how many modes or n numbers should we have? So these are some general ideas. The first thing is that n will be chosen in powers of 2. So it's like 2, and then it's like 4, 8, 16, and it goes like this. That's why you see 4096 in the paper. It's related to the FFT, fast Fourier transform algorithm, which is generally relies on this fact, the powers of 2. Second one, the lowest wave number. We saw this. This is the lowest wave number that corresponds to the largest eddy inside this domain, this cube, and uh, this is K0, which is equal to 2 pi over L. And then you have the highest wave number, which is K max, and it is n times pi over L. And the smallest grid spacing, delta x, in the physical space, it is L over n. So in the spectral space or in the wave number space, it corresponds to pi over k max. And through Kolmogorov hypothesis, we know uh, how to estimate the smallest scale. So we also know how to estimate largest length scale through the integral length scale. So we can have estimation on L, we can have estimation on N as well. But the first question is, what is L? What is this side length? The side length heavily depends on the flow field that you are going to simulate. For isotropic turbulence, a reasonable lower limit is 8 times L0. And L0 is your integral length scale. So why I say lower limit? Because we don't want to simulate a gigantic cube. We want to find the smallest cube size that we can simulate, the smallest cube size. The reason actually is explained in this figure that you see. In this figure is from chapter 6. It's figure 6, yes, figure 618 of Pope's book. So in here, they obtained an experimental data, and it shows the distribution of energy, distribution of energy that is normalized by uh, wave number, and also L11, which is integral length scale. Considering the largest eddy, I mean the smallest wave number, equal to, we said that the smallest wave number is k0, and this k0 was 2 pi over L. You can write that k0 times L0, it is 2 pi over L times L0, and then if L0 is L over 8 based on this isotropic turbulence, it will be obtained approximately equal to 0.8. So it says K0 L0 is approximately 0.8. The x axis is actually this thing, K times L. And if you check 0.8, this is 0.8 in here. This is marked with a line, with this red line in this figure. So this means that if you include all the wave numbers, I mean K times L values that are larger than 0.L, you're actually resolving most of the energy in the flow field. So the only remaining part is this red part in here. And that means that your grid in physical space and your number of wave number modes in spectral space are enough to resolve most of the energy in the domain. Not all, but most of the energy in the domain. In other words, when you say you are doing DNS, you're expected to resolve actually this much of energy. So even DNS is not resolving the whole energy, but actually it resolves most of the energy. This is a very small amount of energy that you cannot resolve. So we already know that what is L in here. It's 8 times L0. L0 is the integral length scale. And you are able to estimate the integral length scale.